thanks a lot, and welcome to this talk on the autonomous quantum processing unit. First question, can you guys hear me somewhat well? Good. Then, to those of you that I haven't met yet in person, my name is Florian. I'm from the other side of the Alps in the beautiful city of Vienna, doing my PhD with Markus Huber. And for the next 15 minutes or so, I'll talk to you about the recent project we've been working on. Now, to say a very brief caveat already at the beginning, the question of autonomous computation is one where we're by no means the first to investigate it. Namely, if we go back to the 1800s, Charles Babbage, here sketched in this beautiful image by Sidney Padua, has already envisaged such an analytical engine for classical computation, where you have some machine where you input your program in terms of a punch card, and the machine does the computation on its own, and after a long enough time, you see the output of the computation. Now, already in that classical picture, there was somehow a steam engine powering the entire computation, also hinting towards what I want to get across in this talk, namely that for a computation, you always need to invest some thermodynamic resources. Now, we want to take this image and transport it into the quantum realm and look at the autonomous machine for computation in a quantum sense. Now, the question is, why do we care about such a, say, thought experiment? The main reason we want to look at this is to understand from first principles what is the energetic cost of a quantum computation, in the sense of, in a standard quantum information theoretic treatment, you often have unitaries which are considered energetically to be energetically free, or a unitary simply costs the amount of energy that you change on a target system, but as we've seen, for example, in today's talk by Yasser Omar, is that somehow there's an overhead cost which we need to account for. And the question is, can we build somehow such a quantum machine where all the parts that are necessary for the computation are contained within that same description, and then allow us to find an account for the thermodynamic cost of a quantum computation. So this is the endeavor that we are going to undertake. And before we get properly started, I want to introduce this concept of autonomy in a bit more detail. And you should think of it as a prepare and forget mechanism, where you have some machine, your computer, and the only thing you as an external agent do is you prepare initially the state of that machine, and then you just let it run on its own without external intervention. Because if you somehow remove that external intervention, you can also avoid that you obscure certain thermodynamic costs by introducing these external agents. Now, for the quantum computer, I'll sometimes refer to the term AQPU, which simply means Autonomous Quantum Processing Unit. And we try to think of a system where we initialize some qubits, initially in a well-defined zero state, and we have some program state prepared initially, then we let it run, and hopefully, after a long enough time, we get the desired output of the computation. So that's the goal for the next 10 minutes that are remaining, and if you're all happy with that, I would continue. So the rough outline is autonomy. We've started looking at this. I will now also start introducing clocks, which are an integral part also mentioned by Misha yesterday for computation, programmability. We'll combine this together at the end, and then I'll draw some conclusions. Now, going again back to something I think is familiar to most of us, the traditional circuit picture for quantum computation starts in all initialized 0 qubits, which Lindsay was yesterday telling us how one could potentially arrive at such an initial state, and then you do a sequence of unitaries. Now, you need a clock to apply this set of gates in sequence, but you also need a clock to do each individual unitary, and that's a key step to realize where thermodynamic cost enters the game of quantum computation. Namely, unitaries, the way they arise in practice is always through some Hamiltonian that is applied for a fixed amount of time. Now, in a computation, you want to have a well-controlled unitary, so you need to turn on your Hamiltonian at a specific time, and you need to turn it off, ideally at some well-defined time tau later. Now, a perfect clock would get these times right. In practice, this is not possible, so you're going to miss the right time according to some probability distribution and end up with the wrong result. Now, how we can quantify the quality of our clock is by using the tick probability distribution of our clock, for example, which somehow tells us when the clock ticks. It has some mean value, it has some variance, the width, and for a good clock, this distribution should be as sharp as possible. You can quantify this with the clock accuracy, which is the ratio of average squared divided by variance. And this has a particularly important meaning, which I would like you to take away from this presentation, namely that clock accuracy defined in this way tells you how many times does such a clock tick until it goes wrong by 1 tick on average, given that the tick sequence is IID. So it has a nice intuitive meaning. The larger this number, the better the clock. Now, since I wanted to present to you an autonomous quantum model for computation, here is a potential way how to implement such an autonomous quantum clock. You could think of say, ring of spins with a single excitation traveling clockwise around that ring coherently, and every full revolution will give you or will count as a tick of this clock. Now, to ensure that this excitation travels around clockwise, you need to break time reversal symmetry, and one way to do this is to introduce a thermal bias, and in the end, this is the origin of a thermodynamic cost for this clock. So somehow having a clock will introduce a dissipative cost. And for those who are a bit more mathematically inclined, the description for this could work in the way that you split your clock into a clockwork part, into a counter part. Now, an ideal clock will go up like a perfectly regular stair. In practice, you will have stochastic fluctuations. So you average overall possible trajectories and get a density matrix description for clock plus counter. Now, as simple theorists like me like to use, one can describe the evolution of such a clock with a quantum master equation, which the reason why we choose such a master equation description is twofold. One is mathematical convenience. The other is in the weak coupling limit, where the master equation has some coherent part for the evolution, has also some dissipative parts of the evolution that generate the ticks and drive the clock. There is a well-defined notion of entropy. So the thermodynamic cost we all care about at this conference can, in this model, be accounted. In this model, we can account for that cost in a rigorous and well-defined way through entropy dissipation, which is essentially the heat exchange with the thermal environments interacting with that clock. Now, in practice, this can be hot-cold baths, this can be voltage gradients like we would usually have in practice. This is all to say that if we have such a specific model, we can relate clock accuracy to dissipation. Now, for stochastic clock models, clock accuracy is upper bounded by entropy production divided by half, which essentially tells us that if we want to have a high clock accuracy, which is useful for a computation, we need to have high dissipation. Now, if we use some more quantum models, we can go beyond that scaling. For example, you can have quadratic relationships, but even exponential relationships appear to be possible. Now, we've had the clockwork part of the whole computation, and I'm burning through my 20 minutes, so let's go back to the computation part. For the autonomous computation, we want to do any unitary. For this, let's look at the universal gate set, which can also be written as a universal set of Hamiltonians, which generate these unitaries if the Hamiltonian is applied for a strict amount of time tau. Now, the unitary can be decomposed into a product of such elementary unitaries, which we then want to be timed by our clock we talked about before. So the program, which is now a sequence of these elementary gates, could be encoded in a quantum state, in principle, where each factor of this, what I now call a punch card state, encodes the step that is done, the Hamiltonian, which should be applied at a specific step in the program. Now, a slightly overcrowded slide, but very important that you follow me, because this is somehow the wishful thinking we should have in mind when trying to come up with a model that realizes such an autonomous computation. Namely, we would like to think of an initial time where we prepare our system. This is the preparation phase, where the clock register, the clock counter is in 0, the target system is in its 0 state as well, and the punch card encodes the program you want to carry out. Now, we want the interactions to be such that if the counter is in 0 and the punch card says Hamiltonian A1 at time 0, a Hamiltonian HA1 is applied on the target system for as long as the clock doesn't tick, but when it ticks and jumps to the counter 1, we would like the second Hamiltonian to be enacted on the target system, and so on, such that at the end we ideally have our desired computation, of course up to approximations due to the imperfectness of our clock. Now, the Hamiltonian which realizes this wishful thinking on the previous slide looks like this. It's a three-body interaction which you can write down on paper to look like this. We have a projector on the tick register, on the program, and finally we enact the corresponding interaction on our target system. Now, the following slide combines all the interactions. The takeaway from this slide here is that within a quantum master equation formalism, we can find a self-contained description that describes the evolution of our system. The details are not that important. All this is to say that if we initialize our system in the state described before, we let it run for long enough with 0 external intervention, and we again look at the target system state after a long enough time, we can figure out how well our target state approximates the desired state of the computation that we want to have. For this, we can look at the overlap of our actual state we end up with the desired state psi that would be the result of our ideal unitary being applied to the initial state. Ideally, the fidelity would be close to 1. To quantify how close we are to 1, we can look at, for example, the infidelity, so 1 minus the fidelity, the error, and an upper bound on the error is given by the following expression, which, now it's again important to listen to these expressions that appear, contains the fraction of the length of your program divided by the clock accuracy, where the clock accuracy was, as we've had before, how many ticks of your clock can you trust until it goes wrong by 1, which is weighted with the length of the program. So, of course, somehow the length of the program should not be longer than how many ticks you can trust your clock, and somehow this enters in our upper bound for the error. There's an additional contribution coming from the types of Hamiltonian, so the magnitude of the Hamiltonian also plays a role in the error. Now, I think I've burned through all the talk time, so I also want to reserve some time for questions. I skip not through that part. So this one part is important because it combines our previous result with results on the clock accuracy. Very quickly, at the beginning, we were saying clock accuracy is related to dissipation. So large clock accuracy requires large dissipation. These are somehow the first relationships, but now we found a relationship on clock between the computational fidelity between the error and the clock accuracy, telling us that small errors requires high accuracy. Combining these two bounds tells us that high fidelity, so small error, requires a large entropy dissipation and gives us a self-contained quantum description of a quantum computer which somehow relates fidelity to thermodynamic entropy and thus thermodynamic energetic costs. Now, the part I wanted to skip through is the following minimal example of how one could find interactions in nature that realize such a behavior of that interaction Hamiltonian I was showing to you before. If you're curious about how such a minimal model looks like and works, I'm happy to supply details. I'm here for the rest of the week, but now I'll run through that and conclude that without dissipation, we have no computation, and I thank to all of you for listening, and I'm now super happy to answer all the possible questions you might have. Thanks.
Thank you. We have a few questions. Time for a few questions. Yes.
So I think you model the interactions as jump operators, right? Not incoherently for the things, right? And I think your results probably would change a lot if you model these coherently. So So I think, like for example, in the talk we heard earlier, it was coherent, model coherently, right? The interactions from this first.
Yeah.
So I think that would make a big difference to the outcomes you get.
Absolutely. So what Misha is pointing out here is that the jump from our clock register from 0 to 1 and so on, that this is an incoherent jump. Now, in principle, one could envisage a way where these transitions are done coherently, and this could also allow for an improvement of this relationship between fidelity and entropy dissipation, because you somehow avoid these dissipative jumps. So this would be possible, I think, would lead to
and I think
an
another
interesting
thing
change of the result.
Yeah, and I think another thing as well, right, is that this fidelity you talk about is also a bit about when the gate was applied, right? We have a stochastic jump. And so for time, this is ultra important if you want to use it to tell the time, right? Because you really care exactly what the time is, right? But for gates, you want them to be applied sequentially. And unless there's something else going on, I think you really want to make sure it's done in a time window that's non-overlapping, right?
Yeah.
So there, it's a different, the fidelity will be slightly different. So like, after a certain time interval, what's the fidelity of which the gate has been implemented, right? Whereas this is, I think, it's more about the fidelity and when, at what time.
Yeah. So it is this interplay between, you need to have a clock to timer individual gate, but then there's also the sequence of gates where you also need to have a bias in that counting process such that you go from gate 1 to 2 and so on.
Right, but they can be conditioned on the previous gates being done, and then maybe it's not so important, I think.
I didn't fully get the last part, but maybe we can try to chat over lunch.
Okay.
But thanks a lot.
Yeah.
Thank you. Thanks for the presentation. So it's the first time I'm hearing this paradigm. My question might be bad, but you will tell me. I didn't get the point of having a quantum clock, because if you just consider your clock to be classical, you have gate-based model of computation and what current hardware is doing. And so what's the added benefits of having a quantum clock and then using this paradigm?
So at the moment, it's only about somehow having, say, a self-contained description for a clock, which could very well be classical. So the formalism works just as well with having a classical clock if you somehow can account for the thermodynamics of it. Because related to Misha's comment, the coupling is done with this incoherent register. The benefit of potentially using a quantum clock is that they could be energetically more efficient, somehow related to this relationship between clock accuracy and entropy dissipation, which could be better for quantum clocks. But the model doesn't really rely on a specific choice of either of the two.
Okay, got it.
But thanks a lot for a good question.
So, the very last question.
Thank you. Okay, so now, I'm a bit confused by the use of the word autonomous here. In my mind, autonomous is I take a closed system, I let it evolve without no external interaction. But actually here, you are using Hamiltonian, so I can imagine laser fields or whatever you want to use to interact with the system. So in this sense, it's not autonomous. In your use of autonomous, you mean you're not doing error correction, you're not measuring the system. Is this what you mean?
So by autonomous, what I want to express with that is that all possible interactions with environments are only interactions with thermal environments. So it could be, for example, a fixed DC voltage bias or a thermal gradient with different temperatures.
What about the Hamiltonians you're applying? Because you want to apply specific Hamiltonian for a certain thing. And these are laser fields or something that comes from outside on your system.
So within that description, the condition on autonomy means that these Hamiltonians are time independent. So these should be fixed Hamiltonians, ideally describing the natural dynamics of a system, but not depending on some time parameter t.
Okay, then how do you switch them on and off?
The switching on and off would be then realized by this Hamiltonian taking such a form where you have conditional interactions. And now the clock, which is a dissipative process, should jump through this counting register through say, a decay process. And through this jump process, you can ensure that a Hamiltonian is switched off and the next one is switched on. But this is somehow then controlled by the counter.
Thank you very much. Thank you.
Hope this clarifies, and thanks a lot for the question. Thanks.